So you got Mr. Murray here, and
Mr. Duggan as well. Hello, children.
We're not going to appear in the video because, well, it's my hands.
There's mine.
So this is Red Elk. He's going to throw the ball from the roof of a building because he gets up to crazy stuff, right?
He's everybody's favorite elk.
And this building is 21 meters tall. And the ball lands out here 17 meters from the base.
And there's one thing that's kind of funny about how these problems get worded. Kids always mix up which one is the height of the cliff and which one is from the base. When we say from the base of the cliff, isn't the base of the cliff right here?
There you go.
That's the base of the cliff. So from the base of the cliff, that means how far out it was. The cliff height is how tall the cliff is. So you gotta make sure that you got the right number in the right spot.
So anyway, this guy's he's gonna start off here with some purely horizontal velocity, right? And that velocity is going to stay constant. Whatever that is the same velocity all the way down. The vertical velocity is going to get faster and faster. So here we have no vertical velocity. Here we've got maybe the same horizontal velocity, but we have some vertical velocity. Here, same horizontal velocity, and even greater vertical velocity. So the vertical velocity is going to get faster and faster. Horizontal velocity is going to
stay the same the whole time. Now, everybody will say, well, what about the air friction? Yeah, we know about the air friction.
We're going to ignore
in real life, it does slow down slightly.
So
but
this is always true in any projectile motion problem, right, is that this acceleration is 0 without air friction, right? This is going to be negative 9.8, okay? Now, if this side is 0, if that acceleration is 0, then these guys are always the same. There really is just one velocity. If it can't change, whatever it is, it always will be.
That's exactly right. Now remember, we call this a T-chart. And you always set this up, and it's just like what we did in the how far problems, except now we have the horizontal, that's why it stands for H, and then we have V for the vertical side. So you see how Mr. Murray put a 0 for acceleration here because the velocity doesn't change horizontally. So in other words, you can also call this average velocity, and that works out great too, and we'll know what that is. We'll get to that figured out. Acceleration, it's always in the air, and so vertically the acceleration is going to be 9.8 meters per second squared. You can count on that. You can take that to the bank.
There you go. And then the other thing that's always true is that the time is always the same on both sides. So you've got to treat these guys separately when you do it. But the only thing you share is time. In other words, it stops moving up and down at the same time it stops moving side to side.
We say that this is like a semi-permeable membrane. You know, normally you got to keep them separated.
That's right.
But time is on both sides.
Time is on both sides.
Yes, it is. Time goes on both sides.
So this is always true. These are always the same, and then the rest of it is you just got to read the problem. So 21 meters tall, that's a vertical thing. That means our displacement's going to be down 21 meters from the top to the bottom.
Negative. You guys see that? He put negative in front because he's going in the downward direction.
And then the horizontal velocity, or the horizontal distance there goes there, so it's positive 17 meters. Okay, and then this is a trick. Because it's a purely horizontal velocity, the initial vertical velocity is 0. Okay, I call these problems cliff problems. It's kind of a special type of problem. Okay, that makes this side pretty simple. We've got this, this, and this. And if you recall, that's all you need to solve everything on this side. So that's what we're going to do. The first step is write the stuff down. Second step is just start solving these things. Okay.
Now, with this, one of the things that you're going to figure out in these problems, and Mr. Murray is going to move up the thing here in a little bit so we can see this, but how these problems end up working out is you will either know the height of the cliff or the time in the air. And that's the key. If you know the time in the air, you can figure out the height of the cliff.
And vice versa.
And vice versa. If you know the height of the cliff, you can figure out the time in the air. And we're going to do that, but first we're going to figure out what the final vertical velocity is.
We're just going to pick these guys off, right? So this thing is, I'm just going to use this guy, right? Let's solve for that. I'm going to use no t, right? So that's 0 squared plus 2 times negative 9.8 times negative 21, right? That's VF squared, so VF is the square root of that, right? So you can do that in one swell swoop. We're going to do that on the calculator. So square root parenthesis 2 times negative 9.8 times negative 21.
Close the parentheses.
Close the parentheses. Don't forget to do that, right? Notice that there's 2 minus signs in there. You can leave them both out. And we get 20.28 meters per second. But remember, this is the
down direction.
It's going down, so you got to put a minus sign on that guy.
Yeah, because if you take a square root, it can be a positive or a negative. You have to be smarter than the square root and know that it's going in the down direction.
Right.
So it's negative 20.28. And just go ahead and leave those extra decimals for now.
And then let's find the time. I'm going to choose, we could find time a lot of ways now, but I'm going to use this guy. X is VI t plus 1/2 AT squared.
Hey, we should go 20.29. Look at your calculator.
Oh, 20.29, there you go. Okay, so we can plug this in. Normally this is very hard to solve for the time, but since the initial velocity is 0, it's actually pretty simple. So we can go minus 21 is equal to 1/2 times negative 9.8 times t squared, right? So I'm going to go negative 21. I'm going to multiply by 2 to get rid of this guy. Divide by negative 9.8 to get rid of that guy. Right? And I've got t squared, and then I'm going to square root that. So square root of the answer. And the time is 2.07 seconds. 0.70 seconds.
Okay, now as soon as you get the time, remember, time goes on both sides.
Just
yes, it does.
Castle that baby across.
Bring it on over.
Now, this side that was unsolvable is now solvable. The only formula you ever use is just, what is it? V is x over t. This is the average velocity, right? Okay. So you could just do this. To find the velocity, we're just going to divide distance over time, right? So we're going to go 17 divided by 2.07. That's meters, that's seconds, right? So 17 divided by the answer I just got. And that's 8.21, we'll say 8.212 meters per second. And then this one's the same.
Because it never changes.
So to start with, we're moving 8.212 over and 0 up and down. At the end, we're going 8.212 over and 20.29 down.
So at this point, we've solved for A. We got our time.
Yep, time in the year is about 2.1 seconds.
So now notice that we reported as 2.1 there for significant figures because we got two figures, so that's all good. Now here's the trick. It says, what's the velocity of impact? We're talking about right before it hits the ground.
Kids always want to say 0.
It's 0. Well, yeah, I know. After it stops rolling around and stuff, it's 0.
So we're going to take this guy.
When we say impact, we're talking about right before.
So let's take that guy and make a vector.
Yeah, you're going to make a vector. So the across velocity is horizontal, which is 8.212.
8.212, right?
And then we got the down and just put 22.29. Kids always go, how come it's negative here and you didn't put negative there? We did put negative there.
It's, yeah, the arrow's down.
Yeah.
Right?
And I always like how when I make the student noise, it always sounds all whiny.
It does.
How come? Well, it's not that whiny. It just...
So that magnitude, we're racing the clock here. The magnitude is 8.212 squared, the square root of, right? The square root of 8.212 squared plus 20.29 squared. so 8.212 squared plus 20.29 squared, right, is equal to 21.89 meters per second. This is also known as the speed. If somebody says, what's the speed of impact?
That's what we're talking
You would you would quote about 22 meters per second. Okay, and then we've got to find that angle there. So that angle there is going to be the inverse tangent
opposite over adjacent
of 20.29
over 8.212.
8.212.
So let's figure that out real quick.
20.29 divided by 8.212. And that's 67.96.
Yeah.
Okay, so you would say that it hits at about 68 degrees below horizontal at a speed of about 22 meters per second. Okay, there you go. If they say speed, you just say 22 meters per second.
And there's the angle, and that's all good, boys and girls.
So fill it in, solve it. You might have to do some vector stuff.